Welcome to the deep dive. Today we're taking on a big one. We're going to explore what makes life tick.
Yeah, we're really going beyond the simple textbook definitions of living systems.
Right.
And we're diving deep into that intricate web of relationships that define life itself.
And to help us along the way, we'll be using Fritjof Capra's The Web of Life as our guide.
Oh, it's an incredible book, truly. Packed with historical perspectives, scientific breakthroughs,
Oh, yeah, I was going to say.
and even some real philosophical nuggets.
It's really exciting stuff. And, by the end of this deep dives, I think we'll all have a much richer understanding of what makes living systems so fascinating,
Oh, absolutely.
from the tiniest cells to the entire planet. But where do we even begin with something this massive?
Well, it turns out humans have been pondering this question of what is life for centuries. I mean, you think back to the early philosophers, people like Aristotle and the Pythagoreans.
Going way back.
Yeah, way back. They were already grappling with the concepts of form and matter, pattern and substance, trying to figure out how it all fit together to create living beings.
It's amazing to think that those questions have been around for so long.
Mm-hmm.
So how did those early ideas evolve?
Well, there was a period where the dominant view was that the world operated like a giant machine. Thinkers like Descartes and Newton were really key in shaping this mechanistic worldview.
Makes sense in a way, right? Parts working together like a well-oiled machine, but something about it feels too rigid to explain the dynamic, ever-changing nature of life, don't you think?
Yeah, you're hitting on something that the organismic biologists also realized.
Okay.
They saw that living systems were far more than just a collection of parts. You can't just look at the pieces in isolation.
Right.
It's about the relationships, the interconnectedness, and how those relationships create properties that are way more than just the sum of their parts.
Okay, that's where things start to get really interesting. So are you saying they shifted from thinking about machines to thinking about, like, systems?
Exactly. They realized that to truly understand a living organism, you can't just break it down into its individual components. You have to look at the whole system and how those parts interact. It's about understanding what we call emergent properties.
Emergent properties. All right, you've got my attention. What exactly does that mean?
Okay, well, think of it like an ant colony. You could study individual ants all you want, but you won't truly grasp the complexity of the colony as a whole until you see how they communicate, how they divide labor, and how they make decisions collectively.
So each individual ant plays a part, but the real magic happens in how they work together. Their collective behavior, that's the emergent property.
Precisely. You wouldn't know just from looking at an ant in isolation that it could be part of something so complex and organized. And this idea, this shift to systems thinking, started gaining serious traction in the early 20th century.
It sounds like a pretty big change in perspective. Who are some of the key figures in developing this systems thinking? Capra mentions a few names, right?
Yeah, he does. One of the big names in the field is Ludwig von Bertalanffy.
Okay.
He introduced the concept of open systems, highlighting how living systems constantly exchange energy and matter with their environment, which, when you think about it, it's pretty intuitive. We eat, we breathe, we interact with our surroundings. It's all about flow.
It makes you realize that nothing is truly isolated.
Right.
Everything is connected and exchanging energy in some way.
Absolutely. And as scientists tried to understand this flow more deeply, they realized they needed new tools and concepts.
Is that where cybernetics comes in? The science of communication and control? I've heard of it, but honestly, it's always sounded a bit intimidating.
Yeah, I get that. But at its heart, cybernetics is about understanding how systems regulate themselves through these feedback loops. Think about everyday examples like steering a car or a thermostat that's keeping your house at a steady temperature.
So cybernetics is the science behind staying balanced, staying on course.
You got it. And living systems are full of these smaller feedback loops. You get too hot, your body sweats to cool down. Too cold, you shiver to generate heat. It's all about maintaining that stable internal environment.
Wow. So it's feedback mechanisms that are working behind the scenes to keep everything in check. Pretty crucial for something as complex as a living system.
Absolutely. And one of the things Capra points out is that studying these feedback loops in living systems really helped us understand the limitations of that mechanistic view we talked about earlier. Machines usually rely on pre-programmed instructions. living systems are far more adaptable.
Right.
They use these feedback mechanisms to learn and adjust constantly.
So rather than a rigid set of instructions, living systems are more like a dynamic dance.
Yeah.
Constantly responding and adapting.
Exactly. And as scientists dug deeper into these concepts, they hit a wall. They realized that their existing mathematical tools just weren't really up to the task of describing these complex nonlinear systems.
Oh no, math. I'm usually right there with you, ready to zone out. But somehow, I have a feeling you're going to make this interesting too.
Well, for a long time, scientists relied mostly on linear equations to describe the world. But what they realized is that linear equations just couldn't capture the interconnectedness and that constant feedback that we see in living systems. Life is rarely linear, right?
Yeah.
It's more about zigs and zags, loops, and unexpected turns.
Definitely feels that way sometimes. So what do they do? Invent new math.
They had to develop new mathematical frameworks. That's where things like chaos theory and fractal geometry enter the picture. They allow us to see order and patterns within what might initially seem random or chaotic.
Chaos theory, fractals. Those sound intimidatingly complex. How do they help us understand life?
Okay, think about a tree branching out.
Ah.
It looks complex, but if you look closely, you see these repeating patterns, similar shapes at different scales. That's fractal geometry in action. Or consider the weather. It's tough to predict perfectly, but chaos theory helps us understand that there are these underlying patterns influencing its behavior.
So it's not about randomness. It's about finding the patterns and order within complex systems.
Exactly. And the beauty of these new mathematical tools is that they allow us to model and visualize this complexity in ways that just weren't possible before.
I love how Capra ties all of this together, the history, the philosophy, the science, and even the math. It's amazing how these seemingly separate fields can come together to help us understand something as profound as life.
It truly is remarkable, and this is just the beginning. Remember that image of the web, the interconnectedness of it all? Well, we're going to see that web come to life even more vividly as we explore specific examples of self-organization in the next part of our deep dive.
All right, I am ready. All right, I'm ready to see this web of life in action. You mentioned self-organization. What exactly does that mean in the context of living systems?
Self-organization is this fascinating phenomenon where order arises seemingly spontaneously from the interactions within a system.
Okay.
Capra dives into some great examples.
Mm-hmm.
One that really captured my attention was this idea of dissipative structures, a term coined by Ilya Prigogine.
Dissipative structures.
Mm.
Okay, that sounds a bit counterintuitive. How can something be both structured and dissipative? It's like saying organized chaos.
Yeah, that's a great way to think about it. It really challenges our typical understanding of order and stability.
Right.
Basically, dissipative structures maintain their structure by constantly exchanging energy and matter with their environment.
Okay.
They actually thrive far from equilibrium, dissipating energy but using that flow to create and maintain complexity.
So instead of a static equilibrium, it's more about a dynamic balance. I'm going to need a concrete example here, something I can really picture.
Okay, imagine a whirlpool. It holds its swirling form because there's this continuous flow of water, right?
Right.
If you cut off the flow, the whirlpool just vanishes. But as long as water is flowing in and out, it persists as this dynamic structure.
So the flow, the very act of dissipating energy, is what allows that structure to exist. That's a pretty mind-bending concept.
It is, and it has huge implications for understanding living systems. They, too, are constantly exchanging energy and matter with their environment, using that flow to create and maintain their complex organization.
It makes you think about life as a process, a constant dance of creation and dissipation.
Exactly. And Capra brings up another example that I think beautifully illustrates this dance: the formation of Barnard cells. Have you ever noticed this kind of mesmerizing honeycomb patterns that form in a thin layer of liquid heated from below?
I think I've seen that in like science documentaries, right? Where the liquid starts bubbling in these regular patterns.
Yes, those are Barnard cells. They form spontaneously as the heated liquid rises and the cooler liquid sinks, creating these convection currents. What's fascinating is that the individual molecules in the liquid aren't being directed to form these patterns.
Right.
The order emerges from their collective interactions.
So from simple rules of heating and cooling, these intricate patterns arise. It's like order emerging from chaos.
Yeah.
But how do we even begin to study these complex, self-organizing systems? It seems like it'd be incredibly difficult to track all those interactions.
Well, that's where those new mathematical tools we discussed earlier really come into play. Remember we talked about cellular automata?
Yeah. You mentioned it as a way of simulating complex systems.
Right.
Refresh my memory on how that works.
Okay, so imagine a grid,
Okay.
like a chessboard. But instead of black and white squares, each square can be in one of several states. The state of each square is determined by the states of its neighbors. And there are these rules that dictate how those states change over time.
So it's kind of like a game with simple rules, and from those rules, complex patterns can emerge.
That's the idea. What's amazing is that even with very simple rules, cellular automata can generate incredibly complex and often unpredictable patterns.
So by using these computer simulations, we can start to understand how self-organization actually works, how complexity can arise from simple rules and interactions.
Precisely. And Capra highlights some groundbreaking work by researchers who use cellular automata to simulate something called autopoietic networks.
Okay.
These are networks that are capable of self-producing, which is a key characteristic of living systems.
Hold on, they actually simulated a self-producing network. That sounds incredible. Tell me more.
So one simulation involved a grid representing a system of molecules,
Okay.
including a catalyst that helped create bonds between other molecules. As the simulation ran, those molecules interacted according to the rules forming chains and structures.
And what happened? Did something resembling a living system actually emerge?
So in some of the simulations, the chains of molecules actually closed upon themselves, forming a boundary that enclosed the catalyst and the other molecules. And this enclosure acted like a membrane, allowing certain molecules to pass through while keeping others out. It was, in essence, a self-producing network, a very basic model of a living cell.
That's amazing. It's
Yeah.
like watching a rudimentary form of life emerge right before our eyes.
It is. And these simulations are giving us these tangible glimpses into how life itself might have arisen from non-living matter.
Wow.
It's a testament to the incredible creativity and resilience of living systems.
It makes you realize that life isn't about static entities. It's about these dynamic networks, constantly adapting and evolving. It's a whole different way of seeing the world. But how do we bridge the gap between these simulations and, real-life organisms? How does this understanding of self-organization and systems thinking apply to the actual evolution of life on Earth?
That's a great question, and that's exactly where we're heading next. We're going to explore how these concepts play out in the grand narrative of evolution, from those early single-celled organisms to the complex ecosystems we see today.
All right, let's talk evolution. I'm ready to hear how this new understanding of self-organization and systems thinking changes the way we look at the history of life on Earth.
Yeah. One of the most exciting things about this new perspective is that it challenges that classic picture of evolution being solely driven by random mutations and natural selection.
You mean survival of the fittest, the whole Darwinian paradigm? Not that it's wrong, but it always felt like it was missing something. It didn't quite capture the creative dynamism of life.
Right. Darwin's theory was revolutionary, but it primarily focused on competition and survival. What's emerging now is a more holistic view, one that really emphasizes the inherent creativity and the interconnectedness of life.
So are you saying there's more to it than just random chance and struggle? Like there's a deeper drive towards complexity and cooperation at play?
Exactly. It's like life has this inherent tendency to explore new possibilities, to create these novel forms and relationships. Capra calls this life's constant reaching out into novelty, which I just love.
It does have a nice ring to it.
Yeah.
It suggests that evolution is not just about surviving, it's about thriving, pushing boundaries and finding new ways to exist. Give me some examples of this creative unfolding of life, especially in the context of interconnectedness.
Well, the fantastic example is the role of symbiosis in the evolution of eukaryotic cells, the complex cells that make up plants and animals.
Okay.
They arose from a truly remarkable merger of simpler bacterial cells.
Wait, are you telling me that our own cells are the result of ancient bacteria teaming up? I need to hear more about this.
It's an amazing story. Billions of years ago, the Earth was teeming with these single-celled bacteria, each with its own unique skills and metabolic pathways. Then, through a series of chance encounters, some of these bacteria began living inside others, forming these symbiotic relationships that eventually became permanent.
So instead of competing, they started cooperating, sharing resources and abilities. What was the advantage of this arrangement?
Well, each partner brought something special to the table. Some bacteria were great at generating energy through photosynthesis, while others were better at using oxygen for respiration. By joining forces, they created a more efficient and resilient unit, a cell that could thrive in a wider range of environments.
It's like a biological merger, creating a more powerful and adaptable entity. And this is how eukaryotic cells, the foundation of all complex life, came about.
That's the current thinking. And the story doesn't stop there. Once eukaryotic cells emerged, they continue to evolve, forming multicellular organisms, and eventually giving rise to the incredible diversity of plants and animals we see today.
Wow. So cooperation and this drive towards interconnectedness are woven into the very fabric of life, from the tiniest cells to the grand sweep of evolution. It really changes your perspective.
And here's where it gets even more mind-blowing. Capra points out that this interconnectedness goes beyond individual organisms. It extends to entire ecosystems and even to the planet as a whole. He brings up the Gaia hypothesis, the idea that the Earth itself is a self-regulating living system.
The Gaia hypothesis, I've heard of it, but I always thought it was a bit out there, maybe a little too mystical. But you're saying it fits right in with this systems view of life.
It does. Think about what we've been discussing. Living systems maintain their stability through these feedback loops and self-regulation. The Gaia hypothesis proposes that similar processes operate at a planetary scale. It's like the Earth has its own feedback mechanisms to keep things in balance.
Okay, I'm intrigued. Can you give me an example of how this planetary self-regulation might work?
One example is the regulation of atmospheric temperature. The Earth's temperature has remained relatively stable for billions of years, despite changes in the sun's output. How is that possible? The Gaia hypothesis suggests that living organisms, particularly plants and microorganisms, play a key role in regulating the composition of the atmosphere, influencing things like cloud cover and the greenhouse effect.
So it's not just about the Earth as a physical system, it's about this intricate dance between living organisms and their environment, a constant feedback loop that keeps the planet in this state of dynamic balance.
Precisely. This perspective really challenges us to rethink our relationship with the planet. We're not just visitors here, we're part of the system.
We're part of the crew, responsible for maintaining the spaceship. It's a powerful way to think about our role on Earth.
It is. And it brings us to another profound shift in thinking that Capra discusses, the nature of cognition. We've talked about feedback loops, self-regulation, and systems responding to their environment. Capra, drawing on the work of Gregory Bateson and others, suggests that these processes are at the core of what we call knowing.
Wait, so you're saying knowing isn't just something that happens in our brains. It's a fundamental property of all living systems. Even a bacterium knows something about its environment.
That's the idea. Think about it. A bacterium senses chemicals in its surroundings. It moves towards nutrients and avoids toxins. These are all actions that demonstrate a basic kind of knowing, a way of interacting with and responding to the world.
So it's not about conscious thought or complex mental representations, but a more fundamental, embodied kind of knowing that's shared by all living things.
Exactly. And as organisms become more complex, this knowing becomes more sophisticated. But the underlying principles remain the same. It's about responding to change, adapting to the environment, and quite literally creating a world through our interactions with it.
Well, I'm starting to see the world in a whole new light. Every living thing, from the smallest bacteria to the most complex animal, is engaged in this dance of knowing, this intricate interplay of perception, action, and adaptation.
And as humans, with our capacity for language, abstract thought, and self-awareness, we take this knowing to another level. We create cultures, we build societies, we develop these complex systems of meaning. But it's crucial to remember that we are still part of this web of life, still subject to the same fundamental principles of interconnectedness and interdependence.
This has been an incredible journey. We've explored the history of how we understand life, from simple machines to complex self-organizing systems. We've seen how cooperation and symbiosis have played this crucial role in the evolution of life as we know it. And we've even touched upon the profound implications of considering the entire Earth as a living system.
Capra's The Web of Life provides this powerful framework for understanding the interconnectedness of all living things. It encourages us to move beyond reductionist thinking and to embrace a more holistic perspective on life.
If there's one thing I'm taking away from this deep dive, it's that we're all part of something much bigger than ourselves. We're all connected, and our actions have these ripple effects throughout this web of life. It's a humbling and awe-inspiring realization. Thanks for joining us on this incredible exploration of living systems, and until next time, keep those minds curious.